So the first topic for today is recurrent equations. And applications of recurrent equations for a study of random walks. So let us start with the following example. You assume that you have a random walk S psi n is initial point I plus S psi of n plus psi 1 plus psi 2 plus psi n. S psi of 0 is I, where psi k are independent, identically distributed random variables. Psi k is 1 with probability p, and psi k is negative 1 with probability q, which is 1 minus p. The interpretation of this random walk will be the following. Two persons play a game. So they toss a coin, and with probability p they have heads, and with probability q they have tails. And if you have tails, then second person give one, say, dollar to another, or vice versa. The first person gives $1 to the second. And S psi n is amount of money that has the first person, and assume that the second person has m minus I dollars. And they play until at least one of them is a bankrupt. For example, if so mathematically we consider random walk, and if the random walk hits 0 before m, then the first player is bankrupt. If random walk hits m before 0, then the second person is bankrupt. And the question is this: how to find the probability that the first player or the second player lose all their money? Let me introduce the following instance. Tau 0 is infimum of n such that S psi n is 0. Tau m is the first time when S psi n is m. And the question is, find probability that tau m is less than tau 0, given that you start from I. So this subindex I means that S psi 0 is I. So we want to calculate this probability where I is greater than 0 and less than m. Okay, let's start. At first, I would like to introduce notation. So this probability is xi, and at the beginning, I can calculate two probabilities. The first one is x0, and the second one is xm. Okay, Gennady. Gennady, are you here? Yes. Gennady, what is x0?
x0, I. mm, mm,
So x,
Zero is where we start, and zero.
yeah, we start from 0. And this is probability that tau m is less than tau 0, that you reach this point before this. Okay, if you start from 0, then I think that tau 0 is 0. You already hit this point. So tau m cannot be smaller than tau 0. So x0 is 0. And another question is, what is xm?
1.
1. Yes, sure. If you start from m, then tau m is 0, so xm is 1. And if I is between m and 0, then you make at least one step. And these steps may be up, or these steps may be down. And after this step, random walk is independent of the past. So let me write the total probability formula. Xi is equal to probability that first step is up, so S psi 1 is I plus 1 times probability that tau m is less than tau 0 given S psi 1 is I plus 1 plus second possibility, probability that the first step is down, times conditional probability that tau m is less than tau 0 given S psi 1 is I minus 1. Well, we know that this probability is P, this probability is Q. So the sum is equal P times, and now look, you start from I plus 1. Future steps are independent of the past steps. So this conditional probability is the probability. So we denote it by xi plus 1. We start from I plus 1, and then we wait until we hit m or 0. And this probability is probability to reach m before 0 plus q x I minus 1. So we get a system of linear equations. So let me write this system. x0 is 0, xm is 1, xi is p xi plus 1 plus q xi minus 1. I between 1 and m minus 1. Well, you have m plus 1 linear equations, m plus 1 parameters x0, x1, x2, xm, and theoretically you may solve this system, and you may see that almost all equations except of first and last has the same form. And today I will present the formula for a general solution to recurrent equation. If xi, the size of jump, is not +1 and -1 but more general, then you can also write system of equations, and most of these equations will have the same form. So I would like today to solve the general equation. Assume that we have just numbers a0, a1, a2, am. Okay, assume that they're complex valued. So I will solve the problem in the whole generality. And I wish to solve equation to find general solution to the following equation: a0 xn plus m plus a1 xn plus m minus 1 plus a2 xn plus m minus 2 plus so on plus am xn is 0 and greater than or equal to 0. I will assume that the first and the last coefficients are not zeros. And I will call this system a recurrent equation of order m. So I will always assume that a0 is not 0 and am is not 0. By the way, if you divide by a0, so let me do it like this: divided by a0, divided by a0, divided by a0, and move this to the right hand side and write this, then you may see that if you know m previous numbers, xn minus 1, xn plus 1, xn plus 2, xn plus m minus 1, then you may find easily the next one, and then the next one, and then the next one. So we will, so for example, if we know x0, x1, and so on, xm minus 1, then we may find, okay, at least theoretically, all other numbers of this sequence. And the idea how to solve it is to use generating functions. Okay, for a while, assume that are given, and let me denote by xn the generating function x0 plus x1s plus x2s squared plus x3s cubed plus so on. And I'm going to find x of s generating function, and then I will recover the sequence x0, x1, x2, and so on. Okay, let's start. So let me write all these equations, starting from the first one, a0 xm plus a1 xm minus 1 plus am x0 is 0, a0 xm plus 1 uh, and so on. And now let me multiply the first equation by s to the power m. The second I will multiply by sm plus 1, the third by sm plus 2, and so on. And then we sum all the equations. So let us calculate this. And well, so times sm times sm, sm, sm plus 1, sm plus 1, sm plus 1. And I also want to combine these terms, and these terms. So what will we get? A0 x m times s to the power m plus x m plus 1 s m plus 1 x m plus 2 s m plus 2 plus so on, plus this. We have a1, so a1 x m minus 1 s m plus x m s m plus 1 x m plus 1 s m plus 2 plus etc. plus the last index am x0 s to the power m plus x1 s m plus 1 x2 s m plus 2 etc. is 0. And now recall that we denote by xs this generating function. And we see here xm s to the power m, xm plus 1, sm plus 1, and so on. So this is almost generating function of the sequence xn. So what we have to do to get x of s?
To add x0, x1s, and
Yes, so we have to add here x0 plus x1s to the first power plus so on x sub m minus 1 s m minus 1. Okay, but if we add something, then we have to subtract the same thing. So it's written here, generating function. So a0 x of s minus this polynomial. Let me write it like polynomial of degree m minus 1 of s plus a1. Okay, we see that indices here are different, m minus 1 and m. So if we move 1s outside the parentheses, then we obtain xm minus 1, sm minus 1, xm, sm, xm plus 1, sm plus 1. So a1s, again, here we may see x of s minus polynomial of degree m minus 2, m minus 2, p m minus 2 of s, and which polynomial? x0 plus x1s plus so on, xm minus 2, sm minus 2. and so on. And the last one, so move Sm here, Ams to the power m, and we see that, wow, x0, x1s, this is just x of s. So this is 0. Now, open parentheses, we obtain a0 xs, a sub 1 s x of s, so a0 plus a1 s plus a m s to the power m x of s, and here what it is, polynomial, a polynomial of order m minus 2. Now here a polynomial, oh, m minus 1 of order m minus 2 plus 1, again some polynomial of degree m minus 1. We move this polynomial to the right hand side, so qm minus 1 of s. So the answer is we have this representation, or x of s is equal to qm minus 1 of s, and let me denote this by pm of s, a polynomial, or the polynomial, this polynomial of order m, pm of s. So we have found the generating function of the sequence. By the way, if we know x0, x1, x2, xm minus 1, we can write down explicitly this polynomial. And we know this polynomial. So we know x of s. And theoretically, we may find sequence xn via differentiation of this analytic function. Okay, this way is not nice. There are simple way to expand x of s into Taylor series. And but by the way, do you know how to do it? Some easy way. Okay, another question. Recall analysis, mathematical analysis. Assume that you wish to calculate integral of this ds. How will you do it? Okay, so let me recall you. So sometimes it's convenient to find roots of this polynomial and decompose this polynomial as a product of monomials, Sm. And the first case is more simple case. Assume that all roots of this polynomial are different. Then xs, and please look, degree of numerator is m minus 1. So this is a polynomial of degree m minus 1. And here the polynomial of degree m. So we use partial fractional decomposition, and we can represent this as the following sum: s minus s1 plus a2 s minus s2 plus am s minus sm. And well, these a's are easy to find if you know this polynomial and all s's. The first way is just to sum these fractions and solve system of linear equations, or there are some other ways. So please recall the course of mathematical analysis. Okay, and if you have this, then it's much easier to find Taylor series for this function than for this one. And I would like to recall you geometric series that 1 over 1 minus x is 1 plus x squared plus x to the power n plus so on. Just geometric series. So 1 over s minus sk is. So I wish to get something like this, 1 minus something. So let me write minus 1 over sk times 1 minus s over sk. And this is x. And this is minus 1 over sk times sum. And from 0 to infinity, 1 over sk s over sk to the power n. So x of s is equal to sum I between 0 and m. Okay, ai times minus, excuse me, k from 1 to m times minus 1 over sk. So certain coefficients, bk, times this s over sk to the power n. So let me rewrite this in the following form. Sum n from 0 to infinity, sum k from 1 to m, bk divided by sk to the power n, s to the power n, where these bk are some numbers. And well, if you make this procedure carefully, you can write down explicit form. But we know that x of s is sum of x n s to the power n, and we know uniqueness of the representation. So this is xn. A few remarks. The first one is this. This sk to the power n is in the denominator is not beautiful. So it would be better to have this number in the numerator, or at least some number without fractions. And what are Sn? Sk. Sk is a root of the polynomial a0. So what is the polynomial? Okay. Of this polynomial. So plus a1s plus so on plus am s to the power n is the root of this equation. And it's easy to see that sk is the root of this if and only if number lambda k is 1 over sk is the root of the following equation: a0 lambda to the power m plus a1 lambda m minus 1 plus so on plus am is 0. And then this expression can be written as follows: xn is equal to sum k from 1 to m b k lambda k to the power n o. And this formula is more nice than this one. Sometimes this polynomial is called characteristic polynomial, and this equation characteristic equation. So we have shown that if xn is a solution to our recurrent equation, then there are numbers b1, b2, b3, bm such that xn has the following representation. The other direction is also possible, and it can be shown that for any numbers b1, b2, bm, xn satisfies recurrent equation a0 xn plus m plus so on plus am xn is 0. And here I don't discuss initial conditions. So let me formulate the result. Assume that a0 is not 0, am is not 0, lambda 1, lambda m are roots of the equation a0 lambda to the power m plus a1 lambda m minus 1 plus am is 0, and also assume that, so this is assumptions, that these roots are different. If xn satisfies equation a0 xn plus m plus a1 xn plus m minus 1 plus am xn is 0 for all positive n, then there are coefficients b1, bm such that xn has the form sum k from 1 to m bm lambda bk lambda k to the power where m. So this is the first part of the theorem. And another, for any b1 bm, a sequence this xn is sum bk lambda k to the power n satisfies equation 1. So we proved the first part, and the homework is to prove the second one. And the natural question is the following. What happens if you may have multiple roots? And the answer is almost similar. There is one exception. When you write this partial fractional decomposition, so if you have multiple roots, then, for example, if sk is a root of certain multiplicity, say a, then you will have representation with this s minus sk squared plus so on. Okay, k1, a k2, and so on. A k. Sorry, excuse me. Assume that multiplicity is d minus 1, s minus s. A k d s minus s k to the power d. However, Taylor expansion for these are well known, and let me formulate the general result. Okay, assume that a0 is not 0, am is not 0, and there are roots. So lambda 1 and so on. Lambda, say, d are roots of the equation with multiplicity L1 and so on, LD, L1 plus LD is M, the order of equation. Okay, they're distinct. And if Xn satisfies this equation, then Xn is equal to sum k from 1 to m. Now we have to write a polynomial of degree L1 minus 1 of n times lambda 1 to the power n plus some polynomial of degree L2 minus 1 of n lambda 2 to the power n. Yes, plus so on, polynomial of degree LD of n lambda d to the power n. And the second part of the theorem is similar. Okay, these are minus 1. These are polynomials, and this is degree of the polynomial. And the second part is this. if xn has representation 2, then it satisfies this equation 1. It satisfies equation 1. And again, the homework is to prove this theorem. Well, but it is not so difficult. And now let us consider example when we consider random walk and gambling problem, and our equation was x0 is 0, xm is 1, xi is pxi minus plus 1 plus q xi minus 1 for e between 0 and m minus 1. Okay, at first we may forget even about these two boundary conditions and just consider this equation for I between 1 and m minus 1. And theoretically, if you know these numbers for indices between 1 and m minus 1, then you may find xm, xn plus 1, xn plus 2, and so on. And you can go other direction and find x0 and etc. So let me write characteristic polynomial. Let me find the roots, and then I will find the corresponding coefficients. Okay, let me rewrite. Here is 1. Let me rewrite this equation in the following form: pxi plus 1 minus xi plus q xi minus 1 is 0, or just add one index and consider I plus 1 instead of I plus 2. Well, so the order is 2, and characteristic polynomial is p lambda squared minus lambda plus q. Let's solve this equation and recall that q is 1 minus p. So you may factorize this, and you may observe that the first root is 1, and the second root is q over p. Is q over p, or 1 minus p over p, q over p. Case 1. P is not q, or p is not 1/2, so the same. Then you have two different roots, and then xi is equal to b1 times 1 to the power I plus b2 q over p to the power I. So xi is b1 plus b2 q over p to the power I. We don't know, we have to find this constant b1 and b2. And we have two additional equations, these boundary conditions. So plug 0 for I. So 0 is b1 plus b2, and then consider I is m. So 1 is b1 plus b2 times q over p to the power m. So two linear equations, two unknown constants, b1 and b2, and finally you solve this system, you find b1, b2, and the final answer is this. Uh, xi is equal to q over p to the power m minus 1. Oh, I'm sorry that m is here and m is the order of this polynomial. And the numerator is q over p to the power m minus q over p to the power I. So this is, one moment, no, excuse me, no, this is not true. Uh, oh, oh, yes. If I is 0, then 0. If I is m, then 1. Yes, so this is correct answer. And case 2, if p is q is 1/2, then lambda 1 is lambda 2 is 1. So you have a root of multiplicity 2. So xi should be 1 to the power I times a polynomial of degree 1. So 2 minus 1. So b1 plus b2i. So b1 plus b2i. We have to find b1 and b2 from boundary conditions. So 0 is b1 plus b2 times 0, and 1 is b1 plus b2 times n. So b1 is 0, so this is 0, and b2 is n, and the answer is xi is equal to I, oh, excuse me, 1 over n, I divided by n. M,
Sorry, is it n or
m. So if the upper bound is m, then m. So if this point is m, you start from I, then probability that you hit this boundary before point m before 0 is equal to I divided by m. So if two persons have a fair coin, then the probability of bankruptcy is proportional to I initial amount of money. For example, if I have $1 and you have million, and we play until I or you are bankrupt, then probability that I will be a bankrupt is 1, my money, divided by m, the total money, million and 1. Okay, questions? Okay, if no, uh, the next topic is, so previous equations are called sometimes homogeneous recurrent equations. Homogeneous because you have, or linear because you have zero in the right hand side. And another equation is how to solve the following equation: a0 xn plus m plus a1 xn plus m minus 1 plus am xn is equal to b bn, where a0 is not 0, am is not 0, so the first, the last are not zeros, and bm is known sequence. So the question is how to find xn. And we may do the same calculations as before. So let me check. So what will be different? What will be different? Okay. So solution will be almost the same. And you have to write here b0, b1, b2, and so on. And you add everything here, but in the right-hand side, you will get s b0 as m, b1 as m plus 1. So in the right-hand side, you will obtain s to the power m, b0 plus b1 plus b1s plus b2s squared plus so on. So sm times generating function of the sequence b. And then similar calculations. So sm b of s, you move these polynomials to the right hand side, and the only difference will be plus s to the power m b of s plus s to the power m b of s. And then the question is, okay, find representation, find Taylor expansion, and so on and so forth. By the way, you know this. So the question is how to find Taylor expansion of this. So this is the first idea. And the second idea is this. Probably you know from theory of ordinary differential equations or of partial differential equations that general solutions of non-homogeneous equation is equal to particular solution of non-homogeneous equation, particular solution of non-homogeneous equation plus general solution of homogeneous equation. And we know formula for this. So to find general solution of this, we may guess or find somehow a particular solution of this. And let me write down now a motivation example, and then concrete example when we will guess a solution. And example is this. We consider the same random walk as before, so plus minus 1. and we wait until we hit m or 0, and let x sub I be the expectation of tau 0 minimum tau m. So this sign is minimum and this sign is maximum. So this is just usual notation in probability theorem. So tau 0 minimum tau m is so-called duration of the game. Time duration of the game. So the game ends, so the random walk ends when you hit 0 or m. And let's find some non-homogeneous recurrent equations for xn. And the idea is the same as before. We know x0, we know x sub m, and we will get certain recurrent equations for other xi. The first question, what is x0? Time 0. Yes, x0 is just 0. You start from 0, so no time. And xm? So what is the answer?
Also 0.
Also 0, yes. You start from m. You're already here. So tau m is 0. And for all other i's, the number of steps before hitting m or 0 is greater than or equal to 1. So you will make at least one step. So xi is 1 plus expectation of other steps, expectation of steps before hitting 0 or m, but we count steps from the first one. Count steps after the first step. And there are two possibilities. The first step is up, and then you step from I plus 1. And another possibility, the first step is -1, and then you start from -1. So actually, we do here some conditioning, and the answer is, with probability P, you start from I plus 1, and then you count the number of steps until the hitting. So tau 0 minimum tau m, the same thing. You start from I plus 1, and you count next steps. Plus q and you start from I minus 1. So xi satisfies, well, and you may see that this is xi plus 1, and this is xi minus 1. So we obtain system of equations. Xi is 1 plus p xi plus 1 plus q xi minus 1. And well, let's try to find a particular solution to this equation. Maybe someone of you know or at least have ideas? Okay, so let's guess. Probably sine or cosine or tangents are not good functions to find particular solution to this equation. And the first guess is just try xi is a constant. Who knows? And now let's write equation. C is 1 plus P times C plus Q times C. Well, but P plus Q is 1, so 1 plus C. 1 is 0. Okay, this was a bad idea. Okay, another attempt. Let's try to search equation in the following form. C times I. Xi, C times I is equal to 1 plus P times Ci minus 1 plus Q, oh, excuse me, plus 1 I minus 1. And now PCI QCI, the sum is C times I. And this I cancels out with this. And we get the following. 0 is 1 plus PC minus QC. So Q minus P times C is 1. So C is 1 over Q minus P if P is not Q. And particular solution to the non-homogeneous equation in this case is I divided Q minus P, and general solution of this equation has the form I over Q minus P plus B1, the first root we know, times 1 to the power I, so I will not write it, plus B2 Q over P to the power I. So this is general solution, plus two boundary conditions. X0 is 0, Xm is 0. You plug here, so 0 for I, then M for I, and you'll get two equations, two unknown parameters, B1 and B2, and you'll find them, and this is a homework. Find exact, find the answer. And another possibility, P is Q. If P is Q, then actually we know that if P is Q, then I is a particular solution to so I is a solution of homogeneous equation without 1. So it cannot be a solution to non-homogeneous. So the next guess is take this, and this is the correct answer. You may find C, then you may find representation, and please find the expectation. And the formula in this case will be beautiful. And interesting. But by the way, maybe someone of you knows the formula in symmetric case. For example, if I have $1 and you have million, and the stake is 1, then what is the average duration of a game until bankruptcy? Okay, if you don't know, it's interesting. And the answer is my money times your money. So if I have only one and you have million, the average duration of the game, so expectation of the duration of the game is million. 1 times million is million. Well, certainly I may lose all my money after the first step with probability 1/2. But the fact that expectation is large means that if I win, for example, 2 or 3 times in a row immediately, then probably the time for bankruptcy become much larger, becomes much larger because the average is 0. So we have small fluctuation, and time to hit 0 will be large. So this is the first remark and the first answer. However, there is one more question. Generally, it is not clear that the expectation is finite. Well, in this particular case, it is. It is finite, and well, even if it is infinite, the system is correct. This system is correct. But then you have just infinity is equal to infinity. It can be shown that if you consider Markov chain, for example, with finite number of states, and all states communicate, that then the the average waiting time until hitting certain set or certain state is finite. So this is the result. However, this is not obvious from the very beginning. Well, and we have 20 minutes, and the next topic is Markov chains and their numerical characteristics, generating functions, and so on and so forth. So I hope that all of you know the definition, and further we will consider a Markov chain, Xn, be a Markov chain, time homogeneous Markov chain. We on a discrete state space, so finite or countable state space, discrete state space E, and let Pij be a transition probability. So this probability is probability that the Markov chain jumps to J, given that Xn is Ij in E, and P be a transition probability matrix. So usually E will be 0, 1 to M, or 1 to M, or maybe natural numbers, or maybe integers. So just normal state spaces. So nothing extraordinary. So if you have transition probabilities, then you can calculate all probabilities for Markov chain. For example, probability that x0 is I0, x1 is I1. Oh, excuse me. Sometimes I will write subindex, sometimes I will use parentheses. sorry for these notations, and xn is in. So let me recall you. If you don't know, this is just a simple exercise. Then probability of this is equal to probability that x0 is I0, just probability to start from I0, and times product of transition probabilities from I0 to I1, from I1 to I2, times so on, times probability to jump from n-1 to an. So if you have certain root, then you take probability that you start from here, and then probability of this jump, this, and so on and so forth. So it behaves like a random walk. So you just consider products. In some sense, you have certain independence. And let me also denote by pk probability that you will be in a point J if you start from I in k steps. Or I may write n plus 0 or n plus k here. So the Markov chain is time homogeneous. And by pk is a matrix of transition probabilities in k steps. And I have a question: how to find this matrix? Is there a simple formula?
Yes, just take it to the kth power.
Yes, great, thank you. So result is this. Absolutely correct. And this is important theorem that transition probabilities in k steps, so this matrix is equal to matrix P, transition probability in one step, raised to the power k for all k greater than or equal to 0. For if k is 0, then this is identity matrix. And by definition, Pij 0, so by definition, so let's agree that this is 1 if A is J. So if you make 0 steps and if you stay from I, then 100% you will be in I, and 0 otherwise. So please remember this formula. Now, few questions similar to the case of random walks. And let me introduce certain notations. Okay, notations. Tau sub A. A is some subset of the state space. Is the first entry time is the first time when xn in A. So this is entry time. And sigma sub A, similar formula. Heating time. So if you do not start from A, then tau A is equal to sigma A. Here, this you have to make at least one step and then to arrive to I. And here, any zero also counts. The first question is, you start from I, you have certain set A, find the probability that earlier or later you will enter A. So question 1, find probability okay, xi, probability that tau A is less than infinity, that earlier or later you will enter the set A. So the probability that there exists n greater than or equal to 0 such that xn in A. Question 2. Assume that you have two sets A and B, disjoint sets. And the question is, find probability that you enter A before B. Find the probability that tau A is smaller than tau B. By the way, we have solved this problem for random walks plus minus 1 with probabilities P and Q. And A was a point M and B was a point 0. Okay. Find this. Find this. So this means that there exists N such that xn in A and x0 not in B, so on, xn minus 1 is not in B. In particular, this means that tau A must be finite. And the third question is, again, you have set A and assume that this is finite almost surely, and find the expectation of the entry time to A. So how much time should we wait until we hit set A? And we solved a particular case of this problem for the case when A was 0 and M, and we calculated average amount of time before hitting 0 or M. So let me write the answers. And the proof is similar to what we did. So here, we have to write a system of linear equations. So if A in A, then what is XA? Ivan, so do you know? Probably not.
Sorry, could you please repeat the condition?
So the question is, we want to investigate this problem and assume that you start from A. What is xi? Probability that tau A is finite. Probability that you will enter A.
Is just 1.
Is just 1. Yes, excellent. Well, and if A is not in A, then idea is the same as before. So you have set A, you have a point I, you write the law of total probability, you make the first step. If you go to the state J, then probability to reach A from J is xj, and you will get the following system. xi is equal to sum over all j in E Pij xj. Okay. Okay, I will not prove this result. It's almost obvious. Just the same reasoning as before. For this case, we have two sets, A and B, and we have to distinguish three cases. We start from A, we start from B, and we start from other points. So if I in A, then you start from I. So tau A is 0 and tau B is greater than 0. So probability is 1. So xi is 1 if you start from A. If you start from B, then tau B is 0. Then tau B 0, and tau A cannot be smaller. So the answer is 0. And if I is not in the union A and B, then you make the first step, you make at least one step before reaching A on B, and you write the law of total probability, and you get the same answer. Pij xj sum over all j in E. So if you wish to solve these problems, then you have to solve a certain system of linear equations. One small remark. If point I is not communicated with A, so this means that you cannot reach A with positive probability. So no way. Then certainly xi is 0. So you may know certain probabilities from the very beginning. Well, and for this expectation, again, we have to consider two different cases. If you start from A, then tau A is 0, so the number of steps is 0. If you do not start from 0, then you make at least one step, so 1 plus. And if after the first step you start from J, then the average number of steps is Yj. Hence, the average number of steps after the first jump is some probability Pij, probability that you jump to J times Yj. This is correct. However, if the state space is infinite, say natural numbers or integers, then the expectations may be infinite. Nevertheless, the system is correct. The system is correct. However, you may have equality like infinity is equal to infinity. Let me formulate you one result. So this system is star. And the result is this. The expectation of the entry time is minimal, is the minimal non-negative solution to equation 0. Okay, and let me write here from 0 to infinity included. This is theorem, and the proof you may find, for example, in book of Norris Markov chains, for example. And formulation means this. This is a solution. Okay, we know this. This solution is non-negative. Yes, but maybe infinite. Well, if A is fine, if state space is finite, sometimes you may find a unique solution which is just finite. Then you are done. Then this solution is minimal, non-negative solution. However, if E is infinite, then theoretically there are infinite solutions. There may be non-unique solution to this equation. And the statement is that among all non-negative solutions, there is a minimum. So minimum solution exists. So it attained. And minimal means that if y1 is one solution and say z1 is another solution, that yi is minimal if you have this. For all I, yi is less than this. And it appears that minimal solution exists. Who knows, maybe for certain yi is less than zi, or for another yi is greater than zi. So theoretically, there may be no minimal solution, but the statement is there is. There is and unique.
So some of these solutions can be non-comparable, but still
No.
there is.
So the statement is, yes, there is a minimal, and you compare it with all others.
Okay, thank you very much.
Yes, but in the most interesting cases, there is the only one solution. But sometimes, so this is the general result, and it's non-trivial only if E is infinite. Okay, so the next, our next lecture will be in next year because we have holidays. So let me formulate just two statements, and we will see that generating functions sometimes help to find distributions for Markov chains. And okay, we start with Markov chain xn. We have a subset A. We have this random variable which may be infinite. We don't know. So this is entry time. And I wish to find the generating function. Okay, let me write it like x of s is a generating function of this random variable. So sum of probabilities that tau a is n, you start from I times s to the power n. And please be careful that sum of these probabilities, so these events are disjoint, and some of these probabilities is between 0 and 1. So it may be, theoretically, it may be strictly less than 1 if you never hit A. Well, and we will consider S between 0 and 1. Okay, so now let's try to find the generating function. And well, we consider two possibilities. We consider two possibilities, I in A and I not in A. So if I in A, then tau A is 0, so xi of S is just 1. So probability that tau A is 0 plus probability that tau A is... Okay, in this sum, only first term is 1 and all other are 0. So this case is not interesting. And if I is not in A, then tau A is greater than or equal to 1. So xi of S is equal to expectation of S to the power tau A. But we know that we make at least one step. So let me write this as S1 plus tau prime A. And this is number of steps before entrance to A after the first step. So this expectation is equal to S times this expectation. And we make the first step. And if you jump into J with probability Pij, then you start from the very beginning from J, and then you wait until you reach A. So the formula is this. You start from J, and you have to calculate this expectation. And what is this? This is xj of S. So the formula is S times sum over all J, Pij, x j of S. So let me write down the system. So xi of S is 1 if I in A, and xi of S is equal to sum over J, Pij, S, x j of S. And again, this is a system of linear equations. And if the state space E is finite, then you can find explicitly xi. And if you look here, then and apply, for example, Cramer formula for the solution, that you may see that xi is polynomial of S divided by polynomial of S. So theoretically, you may find xi of S and even the distribution of tau A. And then if you, well, theoretically, you know this system. And what is the probability that tau A is less than infinity? And probability that tau A is less than infinity is equal to sum of probability that tau A is n, and from 0 to infinity. And what is this? This is generating function at the point 1. So if we denote this by xi, then we get from here our system. Xi of s is 1. Oh, not xi. So xi is 1 if i in a, and xi is equal to s is 1. So sum of pij xj if j if I is not in a, is not in a. And the second question, how to find expectation of tau A? But at first, let us differentiate function xi of s. And if we differentiate function xi of s, then we will see that this is expectation of s tau A minus 1 times tau A for s between 0 and 1. Even if tau A is infinite, then you have this equality, but we have to agree that if tau A is infinite, then this product is 0 for s between 0 and 1. So this is simple. And now we know that we may apply, for example, monotone convergence theorem. And if s goes to 1, then these random variables are monotonous in A, and this expectation converges to these. And this, you may apply this theorem in all cases, even if this expectation is infinite. So monotonous convergence theorem works for non-negative random sequences of non-negative random variables. So we know that and now you may differentiate these, and one of the problem is this: differentiate the star. Okay, assume that the state space is finite, then you have no problem with infinite series and the differentiation, and obtain, at least formally, equation for these expectations. Okay, that's all for today. Thank you for your attention, and see you next year